In this video, I'll show how to build and run and validate a 2D wing in SimCenter STAR-CCM+.
Okay, so here I have a new simulation. I want to start by expanding geometry, and I'll right click here and go to New. Now, there's a few different options to create geometry. One, I can import geometry from another source. I can import that as native file formats, Parasolid, IGES, Step, STL. There's a number of different options. Usually Parasolid is one of the best ones. Another option is to create the CAD inside STAR-CCM+, or I can import it from another CAD program and actually link to it. So actually link into exposed design parameters, and those come into the software, into STAR-CCM+, that is. So I can change a parameter and it updates in both programs. Now in this case, I'm just going to import a curve and then develop the geometry inside the software. So to do that, first I need to get the curve. So I'm using a source of data from Aerofoil tools. In that, we have X, Y, and in this case, Z. For Z, I just put in a bunch of zeros. But for this data, it follows from the leading edge across the top of the airfoil back to the trailing edge. So as you scroll down here, you eventually hit 1, so that's the trailing edge. And originally in the data, it jumped back to the leading edge and went on the bottom of the airfoil back to the trailing edge. So I need one continuous curve to work with. So basically I took all of this data and flipped it upside down so that instead of it going from 1 back to 0, it went from 1 to 1 and then followed it back to the leading edge across the bottom of the airfoil. So once I have that data, then and that's just saved as a CSV file, I can right click this, go to Import, 3D Curves, and then I browse to my file. I click the file that I want, hit Open. I'll import it as a polyline and close the curve and hit OK. And once I do that, I have my airfoil. So now I have this Sketch 3D. I can right click this and extrude it. And this looks pretty good. So I'll just keep that as is and hit OK. Now, some controls for the left mouse button. When you hold that down, you can create a point of revolution about that. So here I'm doing the leading edge. This is the trailing edge down here. Right click is pan, and the middle mouse button is zoom in and out. There's also hotkeys, so if I press T for top, there's F for front, and there's S for side. Now one thing that's important is in 2D simulations, you need the geometry to reside on the Z put a 0 plane. If I want to see that, I can click this global plane here, and I can see that this does reside on that plane. I could also see that from that CSV file that I created. Now I do need to make the domain geometry, so I'll actually right click this plane and create sketch, and then zoom out a bit and create a rectangular domain. Now I want to make this about 25 chord lengths out away from this. The chord in my case is 1 meter. I could also use this measuring tool to figure that out. I click once and click twice to see what that distance is. Now, to make this a little bit easier, I'll just change the spacing here by clicking this and set this to 25 and then hit OK. And then when I zoom out, I can just move these and place them where I need them. And then they just click right in place. And then I'll hit OK. Now once I have that, I'll right click this, go to Extrude again. Now I've got to name some of these faces, and this is kind of hard to click, so I want to make this distance a lot bigger. And body interaction, I want to set to none. For merge, it basically Boolean unite the two bodies, and I don't want that. So now I'll hit OK. And once I have that, I have these two different bodies here. So as you can see here, that's my wing. So I'll rename this to wing. I'll just hit F2 on the keyboard. You can also right click and rename if you want. This, I'll just rename it to domain. And then under these, you have name faces. So we'll split this out in just a moment, but for wing, I'll just rename this as wing. And like I said, I'll split this out. So to split this out, what I'll do is right click on these surfaces. Now if you get disoriented, like I can't see where the actual wing is and which way it's pointed, I can come up here and hit transparent, and then I can zoom in and okay, I can see it's going that way. So in my case, I'll hold down Control. So Control, click, click, and click, and those will be my 3 inlets. So I'll right click on that, rename it inlet. I'll flip around to the back, right click this, outlet, and then this face and the other face here, this needs to be named as 2 different surfaces. It doesn't really matter what they're called, so I'll just rename this as 1, rename this, this as 2. And as I've done that renaming, you can see here now all of those different faces. One other thing that I want to do is be able to take this wing and rotate it. So I'm going to right click this and go to Transform, Rotate, and here if I zoom in, you can see that it's rotated this geometry, and it's rotated about the global coordinate system, which is right at the leading edge. I want to rotate this 10 degrees, so I'll change that here. And I don't want it rotated this way, I want it rotated the opposite way. So I'll flip the axis direction to -1 for Z. And then I do want to expose a parameter so that I can go back and change the angle of attack pretty easily. So I'll click this here, hit expose parameter. Now let's just name it AOA for angle of attack. And then I'll hit OK. And I'm good to go here. So I'll hit Close 3D CAD. And now, when I expand this, I have 2 different body groups. I have domain and wing. So I'll hit, or I'll hold down Control, and then right click this, and select New Geometry Part. Now, here I'm going from a 3D CAD model to a tessellated surface. So essentially I'm going to a bunch of triangulated surfaces. Now I won't go into detail, but that is a needed step in order to actually get into meshing. So I highlight that because some people ask about the difference between 3D CAD and parts. I'll accept all the defaults here and hit OK. And now you can see domain wing under parts. Now I'll come down to operations, and the first thing I want to do is subtract the wing out of the domain. So I'll go to New, Boolean, and Subtract. And for the input parts, it'll be both of these. And then for the target part, basically what remains, will be domain. And then I'll select Perform CAD Boolean and tell it to execute, and then hit OK. So once that executes, it spits out a new piece here under parts. So I do it this way because, say if I were to import new geometry up here, I can then feed it down into parts. So I have my new wing geometry, and then I just basically swap it out and subtract, and it'll spit out new geometry. And that new geometry, which is always this piece, will always be fed down into the rest of the setup. So it's a good way to pipeline it instead of doing it in 3D CAD. It makes it a little bit messier. Anyways, the next thing I'll do in operations is go to Mesh and Batch for 2D meshing. This basically identifies that geometry that lies on that Z is equal to 0 plane. So I'll select Subtract, tell it to execute, and hit OK. And once that's done, now I'll go back to operations again for a final time, go to Mesh and Automated Mesh 2D. I'll select the geometry, select the polygonal mesher and the prismatic layer mesher, and you'll see more on this later. And then hit OK. Now, for now, I'll just keep this as is. I won't adjust it, and you'll see why. I'll go through and iterate on the mesh just a little bit so you can see what those settings actually are instead of me just plugging in values. But one thing I will highlight here, you have a bunch of default controls, and this is basically all the global sizing for your mesh. So I won't change this right now. So let me go ahead and move on to the next step. And that next step is to establish the pipeline between parts, so this stuff here, and the rest of the simulation setup. So to feed the pipeline down into the rest of the process, I need to right-click this Subtract. Remember, this is what we're meshing and everything, down into the regions level. So the regions is what is accepting the mesh, and you're applying physics to that mesh in order to get the solution that you want. So assign parts to regions is what I'll select, And I'll change this one setting here to create a boundary for each part surface. That way I have a wing, an outlet, and a inlet. And then I'll hit apply and close. And now since I've done that, now regions is populated with that stuff that I just made, or that I just pushed down to that level. I'll right click Continua, New, and select Physics Continuum. And I'll right click Models, select Models. For space, I'll select 2-dimensional. For time, I'll select Steady. For material, I select Gas. Flow, I could do segregated or coupled. It's 50 meters per second in my case. In this case, I'll just select segregated. Equation of state, I'll do constant density. There's no density changes. For viscous, I'll select turbulent. And then I'll select K epsilon turbulence. And keep in mind, auto select recommended models is on. So when I select this, it'll automatically select a few other things here. Now, there's nothing else to really select. These are additional options. This is everything that has been selected. So I'll go ahead and select Close. Under reference values, one thing to highlight is the reference pressure, and this is just setting the gauge pressure, but this is atmospheric pressure at sea level. And then there's some initial conditions. This one I will change. For velocity, I want to initialize 50 meters per second in every single cell to start with. If I didn't do this, all of the cells would be 0 meters per second. And so I would have to rely on the boundaries to push flow into the domain and wait for that to propagate all the way through. So this will speed it up if I put it to 50 and 0 for Y. So 50 meters per second in the X, 0 in Y. Now I'll move down to regions. And you can see a few things here when I select these boundaries. You can see what it's connected back up to, higher up in the pipeline. And then you can also see the type it's set to. So for an inlet to be set to wall, that's probably not the most appropriate thing. So I'll adjust this to velocity inlet. Now, you have to consider that in physics conditions. For this, it's automatically set to boundary normal. So if I have a boundary, if you think about that top view that we had here, I'll actually create a geometry scene. There's a little shortcut here for that. If I click that, and I set this to transparent, so there's my wing. And remember this, this, and this are inlets. So if I, and by the way, if I click that, it'll highlight it. Anyways, if this is boundary normal, it'll be pushing flow in this way, then pushing flow in this way, and pushing flow in this way. And that's not what I want. I want all the flow to be going across the screen. So for flow direction specification, I'll change this to components. And when I do that, now, and everything kind of follows a top-down approach. So when I change something up here, it usually trickles down to the node below it. In physics values, now I can specify the direction. And the direction, here's X and here's Y. Well, the direction is in X, and that is correct. So I'll go down to the next boundary. Next one, again, for the outlet, this is set to wall. So I don't want that. I'll change that to pressure outlet. And when I do that, I can see the gauge pressure it's set to. So that's fine. And the final boundary here is the wing. It's set to wall, which is correct. We need a boundary layer to develop on that. So that's good. So I'll keep going down. And there's really nothing left to change here. So what I'm going to do now is start messing around with the mesh. If you remember, I said that I kept all the default values. So let me mesh that and we'll take a look at it. So it's already done meshing, produced this many cells. You can see the time it took. Again, I'll come up to my shortcut up here to make a mesh scene, and you can see what this looks like. So let me come back up to mesh settings to make sense of this. There it is, automated mesh 2D, and the default controls. So the first setting here is something called a base size. This is something that all the other settings by default reference. So for example, if I click target surface size, so this is a target size that'll happen at the surface. It's automatically 100% of the base size. So for the base size, what I normally recommend is to use size that you will most commonly see in all of your cells. So in our case, we don't really have a complex geometry. This doesn't even really look like an airfoil. But one of the things that I'll do in this case, just as a rule of thumb, is to take the chord length and divide it by 100. And that will be used as my base size. So in my case, I'll put this as 0.01. And now you can see if I click target surface size again, the 100% of base size has changed to an absolute size of 0.01 meters. Same thing for minimum surface size, and this is basically the smallest size you can get down to if it really needs to refine something, like a tightly curved surface, for example, is 10% of the base size. So this should work as a starting point for the airfoil. Keep in mind that that small sizing now applies to everything. So I do need to constrain these outer boundaries to be larger because I don't want this small size applying all the way out here because I don't really care what happens out here. I really care about what happens around the wing. So I'll go to Custom Controls, New, and Surface Control. And when I do that, under this, I'll click it, and then Part Surface, I will apply this to the inlet and outlet. And once I've done that, under Controls, I have to tell it how to control it. So I'll say, okay, I want the target and minimum surface size to be just one size, but I do want to customize them. So I'll tell it to customize, and then for values, I'll control click both of these. And for the sizing, I know that I want to put it as 3 meters. Now I don't want to have to try to back calculate what that is in my head, so I'll just change this from relative to base to absolute. And so now I can just put in 3 meters, and that's good to go. So I'll go ahead and come up here and hit mesh, and now you can see the largest sizing applied out here, and now we actually have a wing. The downside to this is that here the leading edge is kind of chunky looking. That needs to be refined. It's very faceted. This needs to be refined more. The other one is the boundary layers are not captured enough by what I have here, and these are the prismatic layers that I referenced earlier. We need more layers in here to be able to actually capture the boundary layer. These are too thin, and the other problem is the cell that sits here compared to this cell, they are definitely not really the same size. We want to try to blend this as well as possible between the prismatic cells and the bulk mesh, so that there's a nice transition from these cells to the polygonal cells. So to do that, I'll come back up here and change the number of prism layers to 5. Now 5 is very, very conservative. I should probably put a lot more layers in this, but I'm going to lean in the way of a faster solution. But you could definitely add in more layers to resolve all the way down to the smallest parts of your boundary layer next to the wall, which would really ideally be needed for a validation level study. But this does a pretty good job of coming pretty close in terms of accuracy, but it doesn't take as long to run. So the other thing I want to do is stretch out those layers. So I'll go to prism layer total thickness and stretch it out from 33% of the base size to 100. And what that will do is it'll basically stretch these layers out to be, instead of here, it'll be somewhere out in here, and this outer cell will be much closer in size to this. So let me go ahead and hit mesh on this, and we'll see what it looks like. So that looks pretty good, except that I forgot the leading edge part. So let me go down here to custom controls, and to enable that leading edge refinement, I don't have anything in the geometry that really identifies a leading edge. So I can make an arbitrary shape and say to the software that I want to refine within that shape. So I can do that by selecting a volumetric control. Now the volumetric control is going to ask me, what am I refining within? And I don't have any geometry that specifically calls out this leading edge like I mentioned. So in this, what I can do is go back up to parts, and there's kind of a shortcut to make just simple geometry for this reason. So I can go to new shape part and cylinder, and here I get a cylinder. Okay. Now its position's perfect, but it is a little bit too big, so I'll change this to 0.07. And now when I zoom in, that looks pretty good. By the way, if you ever want to change this view so that you're always top down on it, you can come up here and change the projection mode to parallel. And now I'm always on top of that. Anyways, I'll hit create and close, and then once I've done that, I have this cylinder. So now I can go back down to my volumetric control, and for parts, I can select the cylinder, hit OK, and now it knows what to refine within, but it doesn't know what to do or how much. So I'll tell it that I want to refine the 2D surface measure, and for values, I'll give it a custom size of 50%. So now I can come in here and again hit mesh, and now you can see that what that refinement looks like. So this looks pretty good, especially for refining the stagnation point and then also getting this leading edge. So that's much better. So now as a final step, I want to refine the wake of the body and just these cells that are kind of around this. Now to do that, one of the things that I can do is change the surface growth rate. So it's just basically controlling how fast these cells can grow out in size. So I'll change this from default to user specified, and I'll change it down to 1.2. Now to control the wake behind the body, I can enable a surface control to basically pattern this surface out in a direction and tell it to refine this. So to do that, I can go to custom control, new surface control. I'll scroll down here to surface control 2. I'll tell it to apply itself to the wing. Hit OK or enter on the keyboard. And under controls, I'll give it a wake refinement. So I'll hit the checkmark box on that. And under values, when I click this, I have to give it a distance. In my case, now your scenarios may change a little bit, but I can use the roller icon here and measure out how far I want this to be. I know I want this to be about 4 meters, so I'll change this to 4. The direction is correct, it's in X, which is fine. And then I will go ahead and give it a size. In my case, I don't want to make it too small because it's going to refine everything that's within that kind of patterning. So in my case, I will make this 400% of the base size, and I'll go ahead and tell it to mesh. Okay, so now you can see that patterning all the way downstream, and you can see some nice growth out into the bulk mesh. Now you can always play with the mesh to determine what the best balance of accuracy and runtime is for your scenario. So now that I've completed that, I'll come back down here to where I left off. So I left off right in here. I'm not going to go through derived parts, and there's nothing to particularly change in solvers. In stopping criteria, you can see the maximum steps is set to 1,000 by default, which should be fine for my application. Technically, I won't know until I start solving it what the convergence will look like, and I'll need to look at that to really determine what that is, but 1,000 should be fine. I'll skip past these two and make my way down to reports. So here, I'll right-click this, go to New Report, and under Flow Energy, I'll go to Force Coefficient, and this will be my coefficient of lift report, so I'll rename that. Now, for a coefficient of lift report, that should be in Y for the direction, so I'll put in 0, 1, 0, and then force option, pressure and shear, that's fine. The reference pressure is 0 pascals, that's fine as well. The reference density in my case is 1.2034, so I'll put that in. The velocity is 50 meters per second. And then for the reference area, that's going to be the planform area, and I actually have to run a report in order to get that data. Now I can actually, the cool thing is that report I can integrate directly into this, so as I change an angle of attack, I don't really have to worry about manually plugging in this number every single time. So let me actually go in and make that report. So I'll go to New Report, Metrics, and Frontal Area. And for this, I'll change the name to Frontal Area Y. For the view up, I'll put this to 0, 0, 1. And for the normal, I'll do 0, 1, 0. So this is X, Y, and Z. And then for the parts, I want to apply this to, under Regions, my wing, and hit OK. Now I can go back to my coefficient of lift report, and under reference area, I'll hit this, and then I'll do that one more time. and this opens up a new option for me. So if I type in report, you can see the two different reports that I have so far. So I can double click the frontal area Y report, and that puts in the language for that. So I can hit OK and hit OK again, and now that embeds that report in the reference area. Now under parts, I need to apply this to my wing boundary under regions and hit OK. And I have my coefficient of lift report. Now I can right click and copy this, or and then come up here and paste. I like it a little bit better to just simply click, drag, and then drop it on the reports, and that makes a copy. So I'll do that for CL to make a CD report, and then I'll just change the direction. So CD would be 1, 0, 0 for X. And then this would need to change, right? Because I need not a frontal area Y report, I would need one in X. So I'll make a copy of frontal area Y, and then change the name to frontal area X. And then when I do that, I would just need to change the normal to 1, 0, 0. So now I can go back to CD and find that area report. There it is. So this is still applied to frontal area Y. So I'll just change this to X, and that should work just fine. Now under reports, the reports, you can right click and run the report. I don't have a solution right now, so it's not going to come up with anything. See, it's all 0, but it'll give you data down here, which is okay. Another step up that you can make is to create a monitor. So I could like right click this and create a monitor from this. In this, as it runs, you'll get data down here, and it's just simple text data, and it'll update every solid iteration, which is better. But to go all the way with this, I can create a plot from that monitor, and that will show me a visualization of an actual plot on the screen. So let me go ahead and do that. So I'll control click both of these, right click, and create monitor and plot from a report. Now, since I did both at the same time, it'll ask me if I want to put them both in one plot, multiple plots. I'll say multiple plots, just my own personal preference. And now it's went ahead and created a CD and CL plot. There's also a residuals plot down here. I won't get into residuals and what they mean, but that's one of the things that it creates by default. Now, moving on down, I have scenes here, and I can see some of the scenes that I've been making. So I can see that geometry scene that I made earlier, and you can also see that mesh scene. I'll make two other ones. This is basically the same shortcut that you saw up here, but I'll make one for a scalar scene. And these scenes are all just templates. The templates have displayers built into them that show like outline and scalar and so on and so forth. But under scalar 1, what I want to look at is velocity magnitude. So under scalar field, I can put in velocity. So just start typing it and change this to magnitude. Now you can really change this to whatever you want. You can change it to velocity in Y, static pressure, whatever you want. But another thing that I want to look at is what the vectors look like. So I can right click, new scene, and select vector. So under vector, again, you have multiple displayers. These can be thought of as layers. You can actually add in more layers to each one of these scenes. So you can layer up different things in a scene and make some really nice visualization. But under vector scene 1, one thing you'll notice in here, actually, sorry, it's here, vector 1, is the display mode is set to glyphs. So they're actual vectors that are shown in the scene. I personally like line integral convolution. It looks like basically streamlines on a 2D plane. I'm just going to use that. And then for parts, it's automatically applied itself to region. And for vector field, it's already started to use velocity. So all that's great. So now that I have that, I'll go ahead and start running this. I'll do some split screens here so you can kind of see how this the run on this evolves. Okay, so I can see CD and CL are not really changing anymore. They've hit convergence. So I can go ahead and hit stop on this, even though we haven't hit 1,000 iterations yet. So I'll hit stop, and I have some experimental data for the coefficient of pressure. So I want to import that in and plot that against my results here. I'll right-click plots here, go to new plot, and XY plot. In this, under parts, I want to apply this to my wing. And I'll hit OK here. For X type, and here you can see this plot. So for X, you can see its direction in X. So that is correct. That doesn't actually need to be changed. So I'll go down to Y. And for Y type, you can see it's set to scalar. And the scalar function it's that I need to set it to is pressure coefficient. So I'll select that. You can see that it's applied to the wing here. Now, one thing to keep in mind is the pressure coefficient. It doesn't have some of the data that is relevant to our case, so we do need to go in and change that. So what I'll do is I'll go to the very bottom of the simulation tree, and when I open this up under Tools, you'll see that there's a thing down here called Field Functions, and if I expand that, I can get into pressure coefficient. And here I can adjust some of that data. So the reference density, as we put in before, is 1.2034. Reference pressure is 0. Reference velocity is 50 meters per second. And that should be good to go for that. So now we can go back up to our XY plot, and this is good to go. Now, one thing that we haven't done here, we've plotted pressure coefficient against this, but we haven't actually imported the experimental data. So to do that, I would right-click Data Series and select Add Data. Now, there is nothing to add here, and the reason for that is because I haven't imported a table yet to do that. So let me go ahead and do that. So if I come back down to Tools, if I scroll down to Tables, I can right-click this, New Table, and select File Table. And once I've done that, I can select the file that I want, select Open, and now I have that table in. So now I can go back to my XY plot, and under Data Series, I can add that in now. So I select the table, hit OK, and now I can see a way to validate my data. So let me get some of these things out of the way so I can see this a little bit better. So now I can see the green dots for the experimental data versus the red dots, which is my CFD. And I can see that matches very well. Now I want to show how to make some changes to the CAD, the angle of attack. Let me collapse some of this stuff. So I can actually come up to the top here and hit Collapse Tree. And the only thing that I really want to look at is a scene of my my vectors. And under Geometry, just so I can see how this changes, under Geometry, 3D CAD, Design Parameters, I have that angle of attack parameter that I exposed before. So if I put this up to something like 19, all I have to do at this point is hit Mesh, and it will update the CAD, the mesh, and feed everything down and through the pipeline. And so you can see that this just changed. You can kind of see a silhouette of our old wing here. So it maps over as well as it can. If you do make a big change, you may want to clear the solution. We can try to run it, in this case, just to see what happens. And it actually did pretty good. Now keep in mind that we're about to hit the 1,000 mark for our stopping criteria, so this will stop once it hits that. So I may want to either come into stopping criteria and change this. I could disable it to let it keep running, or bump the number up, or another thing that you could do is go to Solution, Clear Solution, and deselect this. So it keeps all the solution on the existing fields, but it just clears off the history. So it basically forgets everything that it's done, but the solution's still there. So like I go to my residuals plot, I'm at iteration 0 here, and then I can run. So that's another way to do it. Now if I wanted to bring in new geometry, say I wanted to go in and import a new wing that I have, I could go back into 3D CAD, go to Import CAD Model, and here I have my body that I want to use. So I select this, hit Open, and now I have this new geometry in here, and I'll go to Transparent so you can see it. So you can see that. But I'll close this out for body groups. I'll pull this back down into parts just like I did before. So now under parts I have this. And in operations, all I have to do is in the subtract operation swap out the old wing with the new wing. And then all I have to do is hit mesh, and everything will feed back into the pipeline. So now I have that. Now this looks pretty bad, so I'll go to Solution, Clear Solution, and I will tell it to clear everything this time, including the fields. And when I do that, now I can just hit Run, and it's good to go. Now I'll come up here and I'll hit Stop. If I wanted to automate, say, angle of attack sweep, and then compare that to some experimental data, I could run this one piece at a time, or I could automate the process. Now to automate that process, I could come up here, right click, and select Create Design Manager Project, and then it will build a Design Manager project based off of the simulation that I've built. But this will be the starting point, and I'll go ahead and load a pre-built one so I can walk through it real quick. So in this setup, you can see the pre-built simulation here, all the parameters that came over from the simulation. So this had other additional parameters. So, but this was still a 2D wing that was run. There's CD, CL, so on and so forth. So this is all data that came from the simulation. Now as far as the design study is concerned, if I expand this, you can see sweep was the design study type. If I click input parameters, you can see the different things that you can grab onto. This was just the airfoil angle, so for us it would have been the angle of attack for the last simulation. But here you can put in different discrete values, and it builds this table for you. So those are individual designs that it will test. And then you can look at different responses. So from the simulation basically do you want to track? Well, look at CD, CL, so on and so forth. What scenes do you want to record? What plots do you want to record? So these are all things that you select here. And then there's different settings here. So if you want to run this on multiple cores or multiple simulations at the same time, you can do those things. And then basically from here on down, this is all data gathering after the fact. So here I have a scene snapshot, and then I have a plot. Now the plot was created actually in the design manager. So I created an XY plot here, and I told it to gather my CL data and my angle of attack. So if I split screen this, as you saw at the beginning of the video, I can click these and the scene updates as I click through it. So I can see how the results change as my angle of attack is changing. Thank you so much. I hope you enjoyed the video.